Okay. So what I'm going to do is, first, I'm going to work out the problem partially for the Lagrangian and kinetic energy, potential energy, and then I will actually program that inside the MATLAB. But my hope is that everybody so far is comfortable with the forward kinematics and the inverse kinematics. Did you get forward kinematics working? Forward. So did you get inverse kinematics working? Yes or no?
Yes. Not entirely.
What do you mean not entirely?
I haven't found the like they don't want into D2 and stuff.
Did you use the MATLAB script? Don't try to derive those equations by hand. You can start with the MATLAB script that I gave you for inverse kinematics of assignment 2.
Okay.
Yeah. Did you use the MATLAB script I gave? Okay, good. Everyone is okay with inverse kinematics for the problem? The easiest way to do it is use the MATLAB script that I posted for inverse kinematics of assignment 2. Now, what I'm going to do is I'm going to draw the robot. So, and you can correct me if I'm wrong. So the way the robot is, we have a revolute joint. Then we have a prismatic joint. And then we have a revolute joint. Is this the same kinematic diagram that you have? R, T, R. Do you agree with me? Okay. Now, what I want from you is first and foremost, let's strategize. So you have, this is theta 1. This is D2. And then what you have is, you have, your theta is coming like this, right? The Z, you have theta 3. Now, what I want from you is, if I want to find out the potential energy, and if you want to find out the kinetic energy, let's start with the easiest part. Let's try to find out the potential energy. Now, for the first link, I'm going to represent this as M1. For the second link, I'm going to represent this as M2. And for the third link, I'm going to represent it. So I should not be drawing like this. For third link, I'm going to represent this as M3. Now, tell me, what is this distance? H1. Tell me, just let me just write this down. What is this distance? And tell me, what is this distance? Now, one thing I want you to understand, that these distances should be for all possible values of theta. Okay, so I don't want to see just a number like 0.5. If you give me it's a 0.5, 0.2, 0.3, it's a number, it means that height is going to remain constant throughout the robot operation. So no matter what the value of theta 1 is, no matter what the value of d2 is, no matter what the value of theta 3 is, that height is going to remain constant. With that in mind, tell me what is h1. h1 is 0.5 by 2. Is that right?
Yes.
What is h2?
0.5.
And what is h3?
0.5. 0.5 plus L by 2 minus plus, right? Minus sine whatever that one is. L by 2 sine 2 theta. I got it plus, I don't know.
What 0 point?
Oh yeah, how much?
0 point?
Yeah. Okay, how much? Oh, whatever.
Okay, give me, I know,
Okay.
give me one value.
Okay, 0.5 plus L by 2 sine theta 2. It will be plus or minus depending. Yeah. How are we moving here?
Sine theta 2.
Sine theta 3.
Oh, theta 3. Are you with me so far?
Yeah.
Okay, good. So the potential energy equation is m1 g h1 plus m2 g h2 plus m3 g h3. And what I'm going to do is I'm going to substitute those values here so that when we program inside the MATLAB, we'll directly grab numbers. Yes.
Can we write minus because the convention that follows minus just suits it. If theta will be if it goes down, then it automatically. Oh, sorry. It depends on how you. Yeah. Sorry. Please ignore.
Everyone good with this equation?
Yeah.
So what is m1? Tell me mass m1.
1.
Oh,
1 9.81 times 0.25 plus m2
Same one.
9.81 0.5 plus m3 1
Yeah.
9.81 multiplied by 0.5. What is the value of L?
0.5.
0.5 by 2 sine theta 3. Now next thing is I want to find out the kinetic energy. And I'm going to go step by step. To find out the kinetic energy of mass m1, I need to find out the position of mass m1. How do I find out the position of mass m1? So to find kinetic energy, and actually I'm going to solve this problem very systematically because quite a few students came to me and they told me they understand the Lagrangian dynamics as a whole process, but when they actually start working out the problem, somewhere they get confused. So let me solve this problem step by step. To find kinetic energy of mass m1 or link 1, what we need is to look at 0h1. And I'm going to ask you for something and you'll just tell me that, okay? 0h1 is going to have 0r1. There will be 0, 0, 0. There will be 1 here. And now you should tell me the equation for px. Equation of py. Equation for pz.
1 by 2.
So 0.5. Is this the equation that you have? Everyone good with this? Now please note, this is 0h1, my 0th frame, and I'm assuming you drew your frame like this. And my second frame, it's somewhere over here. So this is my first frame, this is my 0th frame. So the distance from 0th frame to M1, and we have to be in the consistent coordinate system. I'm going to call this Px, and I'm going to call this M1 because this is the distance till M1 is going to be 0. Py, distance from M1 is going to be 0. And this is very important, Pz, distance to M1 is equal to 0.25. Everyone understood this? Now, yeah, because this is at half of distance. Now, what is the velocity? So I'm going to write this down clearly here. Vx M1, and the reason I'm doing this because you will do the exact same process when we go to mass M2. Vx M1 is the derivative of 0, which is going to be 0. Vy M1 derivative of 0 is going to be 0. Vz M1 derivative of 0.25, 0.25 is a constant, is going to be 0. Do you agree with me?
Yeah.
So now what I'm going to do is I'm going to write down here kinetic energy of translation for mass M1 is going to be 1/2 M1 Vx square Vy square plus Vz square for M1. Do you agree with me? Since all these values are 0, the kinetic energy of translation for the mass M1 is 0. What it means is mass M1 is not moving either in x direction or in y direction or in z direction with respect to the reference frame 0. Everyone understood this? Now comes the interesting part. Now, what I want you to tell me is, I'll give you the equation omega x, omega y, omega z, and I will write this expression down here, which is 0 r0, and the rotation is 0 0 theta 1 dot. So what this means, omega x is the angular velocity about x, omega y is the angular velocity about y, omega z is the angular velocity about z. I want you to look at this configuration, and can you see and tell me what would be the value of omega x?
0 is identity matrix.
So 0 or 0, correct, is an identity matrix. So do you agree with me? Omega x is 0. Omega y is equal to 0. Do you agree with me? Omega z is equal to theta 1 dot. Agreed? So before I derive the equation for moment of inertia, here is the next step. I'm going to write down kinetic energy of rotation. And please note, if you just have a point mass, and this is super important, if you just have a point mass and that point mass is rotating, its kinetic energy is 0 because the point mass does not have any lever arm. It does not have radius of gyration. point mass, radius of gyration is 0. That's why it's a point mass. Everyone understood this? However, this is actually not a point mass, but this is actually a link. This is not a point mass, but this is actually a link. And this link has its own Ixx, Iyy, and Izz. In other words, the link has its own mass moment of inertia about x-axis, mass moment of inertia about y-axis, and mass moment of inertia about z-axis. Now, the question here is, let me write this expression down and then we will see how do we find that out. So the expression is going to be 1/2 Ixx omega x square. This is the standard equation. 1/2 Iyy omega y square plus 1/2 Izz omega z square. Now, what I'm going to do is, since omega x is 0, can I say this guy is 0? Since omega y is 0, can I say this guy is 0? So now I'm left with finding out what is Izz. Do you agree with me? Now, here comes the question. How do we find out the value of Izz for a cylinder which is rotating about its own axis? So for that, what you need to do is, you need to look from top of the cylinder. So, and you can have a cylindrical shape, you can have a rectangular shape. So what I want you to do is, I want you quickly, and I'm going to do this exercise just once. I want you to Google and find out the moment of inertia of the cylinder with radius or r, moment of inertia of radius r and length L. And please note, this is the axis we are trying to find out moment of inertia about. And I don't expect you to derive, or I don't expect you to remember. Just Google and tell me what is Izz for this guy.
1/2 ml squared.
1/2 ml square.
R squared. L doesn't matter.
1/2 m r square. Are you with me so far?
Radius is not given.
Okay. So 1/2 m r square. Everyone okay with me? Just for my reference. So remember, if you have moment of inertia about either x or y axis, which means the axis perpendicular to z axis, what would be the moment of inertia? 1/12 m L square. That equation is actually 1/12 m in the parentheses L square plus r square. But since r value is considered to be very small compared to L value, you can ignore that. Now, as I understand, I did not give you the value of r. Do you agree with me? So I'm gonna give you this value of r here. Assume r is equal to 0.1. With that, kinetic energy of rotation can be found out as 1/2 Izz is 0.5. The value of mass is 1. Value of r is 0.1 square theta 1 dot square. Are you with me so far? Yes.
So are we supposed to assume that same value for the homework as well?
Oh, yeah, you can assume the value of r for 0.1. Actually, I'm solving your homework for you, and remember, evaluations are coming. Okay. Oops, it's all recorded. Doesn't matter. Anyway, so kinetic energy for mass M1 is, I'm going to write this equation down. We already have everything. First, translation is 0. Rotation is, can you tell me the number here? 1/2, 0.5, 1.1 square. What is the answer that you get?
Theta 1 dot by 400. Theta 1 dot square by 400. Right.
So next part, I'm going to repeat the same process for mass M2. Now, so to find kinetic energy for mass M2 and link 2. Now this part is really interesting, so please pay attention. So for that, you need to tell me 0H2 0, 0, 0, 1. What is Px, what is Py, and what is Pz? Yes, you can assume that in homework as well. Yeah. Remember last time we had a deal that you will work out the forward kinematics and give me these values. Oh. Eric, what is the answer? What is the answer for Px, 0H2?
I have it 0 H1. Sorry, H1.
Yeah, so
I got 0, 0, D2.
Yeah. What's it?
Sine theta 1. Huh? 0
0, 0, D2 is not right.
No, 0 H2, not 1 H2.
D2 cos theta. Oh,
So minus D2 sine theta 1.
I need 0H2. 0H2 is 0H1 multiplied by H12. Okay.
D2 cos theta 1.
G2
Okay.
D2 cos theta 1.
cos theta 1,
D2 sin theta 1.
D2 sin theta 1, and 1. Right? So with this, I can find. Okay, check this out. This is from up to this. So this is link number, this is the frame number 2. But our mass is at the half of that distance. Do you agree with me? So I'm going to follow the same process. And then I'm going to say Px mass M2 is D2 by 2 cosine theta 1. Px, sorry, Py mass M2 D2 by 2 sine theta 1, and Pz. What about Pz? M2, it will not change. Yes. 0.5.
Yeah, actually that's 0.
Yeah, it should be 0.5.
Somebody gave me 1, right? No?
I took 1.
Okay. Yeah. So we got these PXs, PYs, and PZs. D2 plus 0. D2 PZ is D2 plus minus 0.5. No, I think these values that you have, they are correct here. So now we need to find out the velocities. It is important to note that d2 is a variable, theta 1 is a variable. So you have to use the chain rule. So Vx m2 is 1/2 d2 dot cosine theta 1 minus d2 sine theta 1 dot. Are you with me so far? Everyone understood? This is u times v, u dot v plus v dot u. Same thing here. Vy m2 d2 dot sine theta 1 plus d2 cosine theta 1 dot, and Vz m2 is equal to 0. You guys are with me, right? Okay. Now what I need to do is kinetic energy of translation for mass m2 is going to be 1/2 Vx square Vy square plus Vz square m2. And we would actually grab these equations because everything is a variable. So we'll grab these equations and directly program this inside MATLAB. Now the next part, which is a little interesting, is how do we find out the angular velocities omega x, omega y, omega z, and that is 0r0, 0 theta 1 dot plus 0r1 multiplied by what?
0.
No, got you. There is no d because d is the translational moment. I mean translational velocity. So this is the for just for the angular velocity, right?
0, 0,
So this will become 0, 0, and a big 0. Are you with me so far? Remember this. This is the point where students make mistake. Now what it means is omega x, omega y, omega z for this guy is going to be 0 r0. So omega x is going to be 0, omega y is going to be 0, and omega z is going to be theta 1 dot. Do you agree with me? I will wait here for a second, and before I proceed, I just want to make sure that everyone understood omega x, omega y, omega z, and what does this physically mean? What it physically means is you have this robot arm, and on this robot arm, you have this horizontal arm, and this horizontal arm can go forward or backward. This horizontal arm can only go forward and backward. And if you rotate this, the angular velocity of this horizontal arm, I'm going to call this omega z, is also going to be omega z. Everyone understood this? Now here comes the tricky part. The tricky part here is when you want to find, and this is super important, this is where the students make mistakes. If I want to find out the moment of inertia of link 2, if I want to find out the moment of inertia of link 2, they should be in the same consistent coordinates as our angular velocities. What do I mean by that? What I mean by that is I want you to understand for this point is super important. My angular velocity is about this z axis. Do you agree with me? Everyone understood? My angular velocity is about z axis, which means the angular velocity of the second link is also about this axis. So this is the axis about which you have omega z. Do you agree with me? Now what I want you to do is same logic. Is that a rectangular or is it a circular? The member, the link to
Oh, no, that is rectangular.
rectangular. Okay. So now what I want you to do is I want you to go online and look at the moment of inertia of the rectangular beam, and I'm going to give you the axis about this axis, and I will give you the dimensions. What this dimension is, d or
That
c?
is slender rod, right? It's then will be
Not given.
that will be slender rod, right?
We'll do the cylinder rod assumption later. So one of the dimensions will be
So
set to
the
0.
Lengthwise is given V2. So.
No, I will just write this as L. So
Yeah.
I will just write it. So the I value is 1 by 12, and I will actually substitute the values. 1 by 12 m it is L square plus, actually I will change this because there is another D. I'm gonna call this C. L square plus C square. Do you agree with me? However, now I want you to understand how is it different for our problem. In our problem, unfortunately, the length of that link changes. You agree with me? The length of that link changes. Now, what?
The minus V, the whole square.
So, but there is another assumption here, is if we make an assumption that is the slender rod, then the value of C is significantly smaller compared to the value of L. So since L is much greater than C, L square is going to be much greater than C. So this assumption, this guy is going to be 1 by 12 m L square. Now there are two ways this problem can be viewed, and I will tell you both the ways, the way the problem can be viewed. And that's why this problem is a little bit open-ended. This link D2, it could be a telescopic link. What do I mean by telescopic link? It could be just like an antenna. So it could be a telescopic link where it's just an antenna and it's actually going to extend as it extends. Or this link could be a translational link. So what I mean by that, and this is very important because when you consider values of I, that assumption will actually be very useful. So think about link D2, the link is like a telescopic link. Now what happens with this telescopic link? With this telescopic link, as D increases, the length, the physical length increases. Do you agree with me? As D increases, the physical length increases. So which means if I assume that link to be a telescopic link, my moment of inertia is going to be 1 by 12 md square. Do you agree with me? If it's a telescopic link, like an antenna. Everyone understood this? Now here is the other twist. If I assume that prismatic joint, and the reason I'm saying this is both cases are possible. If that prismatic joint is something like this, it's like a slider joint. It means the link length is like this, but you have a slider like here. It's like a crane. And then this guy is D2. Are you with me? The moment of inertia in both the cases are different. In the case of telescopic link, you will say it is 1/2 1/12 md2 square, because that length itself is changing, but mass is not, because the mass, the same, when it's closed, you have the same mass m. When that gets extended, it has the same mass, but it's more distributed, but that is the same mass. However, if you have a crane, then what you would do is, no matter what is the value of d, your L is going to remain the same. So which is 1I is equal to 1/12 ml square. L is constant and D is changing. So this is like an antenna. And this is like a crane. Yeah.
In case of antenna, wouldn't that also be like a hollow cylinder? So it would be a.
Yeah. So you can make those things as complex as you want. I mean, you can be a hollow cylinder, and your equation for, even if it's a hollow cylinder, you can use the equation for the hollow cylinder for moment of inertia. And the idea is, what I want to tell you is, there are these two cases. In one case, mass moment of inertia is changing. In second case, mass moment of inertia is constant. Both ways are fine. So yeah.
So during the in the crane thing, the second one. So usually we know this thing whenever we have a pretty higher length from the rotation, we have a higher moment of inertia, and when we get closer, moment of inertia reduces. Or is it vice versa? So in the crane, as it is moving back, does the moment of inertia change, or the angular velocity?
No. So let me, okay. So basically, actually, let me answer this question. We are finding the moment of inertia at the centroid of this boom. So our moment of inertia is always at CG. We are not finding moment of inertia as the center of rotation, which is over here. We are not finding moment of inertia at the center of rotation. And actually, there is a long explanation for this. Okay. What it happens is, let me quickly tell you what is going on. And remember this is something fact. Moment of inertia as the center of gravity, mass moment of inertia as center of gravity do not change. Mass moment of inertia which are found at center of gravity do not change. Mass moment of inertia at center of rotation may change. What that means, and because here is something that I want you to think about. Difficult concept. I'll try to explain that in 2 minutes. If you don't understand, that's okay. Imagine the crane is at this distance. The centroid moment of inertia of the crane is the same, but mass multiplied by the radius of gyration is more. That adds effective moment of inertia about the center of rotation. So if you have the crane, if crane is extended, at the CG of the crane, the mass moment of inertia is the same. But when you look at the total kinetic energy, or if you look at total momentum, the moment of inertia at the rotation joint is more because it's mass multiplied by the radius of gyration square. And you know which term will take care of that? Translational velocity will take care of that. If you don't follow, that's totally fine. So to answer your question, answer is that's why we are trying to solve the equation is written at the center of mass, not at the center of rotation. Please note, center of rotation is different. Center of rotation is at joint 1, but we are finding out the kinetic energy at the centroid or mass center of link 2. Everyone understood this? I can derive a very nice half a page derivation on this, but I want you to understand the equation that I have written is correct. How would you do something like this inside SolidWorks? When you are trying to solve a robotics problem in SolidWorks, if you have unsymmetrical object, you click or you select the particular link and then find out the principal moment of inertias. It will actually show you the local coordinate system, the principal moment of inertias in local coordinate system. You have to align that local coordinate system with the inertial coordinate system, because all our angular velocities are in inertial coordinate system, and then find out the moment of inertias. Believe it or not, this is exactly what I did here. I found out the moment of inertias assuming that my z-axis is aligned with the axis that is perpendicular to link 2, shown in green. Okay, so that being said, I'll go ahead and write down the equation for kinetic energy of rotation for mass or link 2. And that is going to be 1/2. Which one do you want me to use? Antenna?
Because I did it.
M is 1, D2 square multiplied by, this is just the value of I, okay? Multiplied by the value of omega, which is θ1 dot square. Are you with me so far? The last part. So did everyone understand the thing that I told you about the moment of inertia at the center of rotation could change, but the moment of inertia at the CG is not going to change? Did everyone understand that or no? Yes, no?
Yes.
That is the reason why when you see the figure skating, they close their arms inside and they extend their arms outside. Because what happens is, here is what happens. The centroidal moment of inertia does not change. Centroid moment of inertia does not change. But by extending the arms and closing the arms, the radius of gyration changes. That changes the moment of inertia about the center of rotation. That's why they extend and they close. And that's why the speed changes, because the conservation of momentum. You understood this? Okay, good. All right, now the next part is kinetic energy for mass, kinetic energy for mass M3. Okay, same drill. Now 0H3. Tell me Px. Tell me Px.
It will be different because I have different axes. That
Here axes are different.
Yeah.
So tell me and we'll check.
okay. Because it will not match. So okay. Minus sin theta 1. Whole multiplied by
Minus
2
theta.
d2 whole multiplied brackets.
Okay.
D2 2d2 plus cos theta 2
This one. This guy.
plus cos theta 2d2
2d2.
yeah 2d2 plus cos theta
2d2 plus cos theta 2.
by 2 whole by 2.
Okay. Is this correct?
That's not what I have.
Okay. What did you get?
For that, I got cosine theta 1
Yeah.
times
My
D2,
second
yeah, times D2 plus A3 cosine theta 2.
Cosine theta.
Yeah, cosine theta 1 multiplied by, in parentheses, D2 plus A3 cosine theta 2, and A3 I think is just L in this case.
Cosine theta 3, right?
Yeah.
Any other verification? What about 10?
Whole divided by 2.
whole divided yeah whole divided.
Whole divided by 2?
Oh, that's not what I have, but
Yeah, so divide, there will be a whole divided by 2.
For center of mass, for 0h3, it would be divided by 2.
Okay. I want 0h3. We will do that a little bit later. So 0h3 px. What is py? Sine theta 1?
The thing which I said. Yeah, minus sin theta 1 for me at least.
yeah, probably.
T2. Everyone is getting different answer.
No, it's the axis right, like x and y. That's
Okay,
all.
last one. What is the last answer? Let's see. Somebody gave me that
Sin
answer,
theta
which
2 by
is
2 plus
D2
0.5.
D2 plus A3 sine theta 3, right?
Yeah.
Other students, you have solved this problem, right? Then speak up. If this goes wrong, it's not my fault because that is the input that you gave me. So now this is for the center of the joint. I mean, so the end effector, this guy. Now the problem is, yeah.
D3 being as part of your PC doesn't make sense. Considering D2 is only
So is it what 0.
A1.
A1?
Plus
A1.
A3 science has been divided.
No, divide 2 will come a little bit later.
No, that's divided by 2 because we already substitute the 0.5. That's why we are saying 0. By divided by 2.
A1 by divided by 2.
A1 by actual value is 0.5. MATLAB is showing that one. That's why we are confused from that part.
What is A3? A3, I think, is the length of the pendulum, right?
0.5.
Yeah.
0.5. So
Everyone are right.
oh man, this problem is taking way too much time than I thought. Cosine theta 1. Do I need to substitute? D2 is a variable. So D2. A3 is 0.5, right? 0.5. Cosine theta 3. Sine theta 1. D2 plus 0.5. Cosine theta 3. And A1 is what? 1, right? A1 is
A1 is
0.5. 0.5 plus 0.5 sine theta 3. And this is 0, 0, 0, 1. Now, what I want to ask you is, we want to find out the distances to M3. These distances are from 0 to h03. So 0h3, which means these are the distances all the way from here. But we want it to M3. What would be the difference for M3? Please note, it would be the first part D2 would remain as is. So Px M3 will be cosine theta 1, D2 would remain as is, plus 1/2 0.5 cosine theta 3. Py M3 is equal to sine theta 1 D2 plus 1/2 0.5 cosine theta 3. And Pz so Pz would be 0.5 plus, and this would be 1/2 0.5 sine theta 3. And why this 1/2? Because please note that link 3 is 0.5. But our mass is over here. So whatever we have here, so this and this guy is to account for the mass which is at half of the link length. Everyone understood this? Now the question comes is, how do we find out the velocities? And the fun begins. Now please note that there are, yes,
For 0h3, it's just the inverse of 0h4 times h2, right?
0h3 is 0h1, 1h2, 2h3,
Okay.
right? I don't think there is any inverse here. Okay, once that is done, then the fun begins. I have to differentiate this entire equation. Easiest way to differentiate, if you don't want to make mistakes, is I will write this down: cosine theta 1 d2 plus 0.25 cosine theta 1 cosine theta 3 py m3 is equal to sine theta 1 d2 plus 0.25 sine theta 1 cosine theta 3, and finally pz m3 is equal to 0.5 plus 0.25 sine theta 3. Now we have to find out the velocities. Px m3. Chain rule. Differentiation of cosine minus sine theta 1 dot d2 plus cosine theta 1 d2 dot. This is the derivative of first term. Then the derivative of second term plus 0.25 in the parentheses. Derivative of cosine theta is minus sine theta, theta 1 dot cosine theta 3 minus cosine theta 1 sine theta 3 dot. Are you with me? So this is the derivative of this guy. Next part, Vy m3. For that, sine theta 1 d2 becomes cosine theta 1 dot d2 plus sine theta 1 d2 dot. So this is the first term. The second term is plus 0.25 sine theta becomes cosine theta 1 dot cosine theta 3 minus sine theta 1 sine theta 3 theta 3 dot. Eric, does it make sense? Did I make any mistake? Good, thank you. VC M3, derivative of first term 0, derivative of second term 0.25 cosine theta 3 dot. Are you with me so far? Huh? Wait till we write the language. And this is just for 3 degrees of freedom robot. In final, I will give you 6 degrees of freedom robot. Oh wait, there is no final for this.
Thank God.
So, so it would be 1/2 M3. M3 is 1, right?
Yeah.
I will just code this in the MATLAB. So Vx square plus Vy square Vz square. Actually, I will show how to code in MATLAB, but once again, I'm not going to upload that code onto Canvas. So
This is recorded, so
yeah, I recorded. Maybe I'll stop recording. Okay, the next part is we didn't find the omega x, omega y, omega z. So omega x, omega y, omega z. Yeah, actually, once you do it systematically, it's to be honest with you, it's not difficult. It is tedious, but it's not difficult. But if you think this is tedious, try solving this problem using Newton's laws. 0, 0, theta 1 dot plus 0 R1. What is here? Zero R2 0, 0, theta 3 dot, right?
yeah.
What?
Yeah.
What? Your theta cannot be in any other direction. The joint axis should match with the z axis. Man, you'll about give me a heart attack. At the end of the semester, you would say that theta is in y direction. So right, 0 plus. Now I don't remember what is 0 R2. You have to tell me 0 R2.
I messed up my right hand coordinate system.
Everyone is using right hand coordinate system.
No, I messed up.
You messed up your right hand coordinate system? Okay, all right. You're looking at it from the left hand side?
No.
Okay, so tell me, someone, please. Eric,
0. No.
why no?
I didn't do this on the paper.
0 R2. I'm keeping my side of the deal, guys. You have to keep your side of the deal.
After 0.
Huh?
0.
0.
Minus cos theta 1. Sin theta 1. 0. Minus sin theta 1. Minus cos theta 1. 1, 0, 0.
Okay, if the problem goes wrong, blame this guy. But before I go further, I want one more confirmation. This is correct. So this is going to be please confirm 0R2. Eric, 0R2, correct? Is it right?
I didn't have this on the paper.
Then open your MATLAB code and tell me.
Same as that. I'll send you an email.
Oh, I can't open your code in front of everyone.
Okay.
Anyone else? You go. Are you sure? Anyone else? Okay, so I'm gonna use this and write down. Okay, Joey says it's right. Okay, good. So sine theta 1, theta 3 dot. Next thing is minus cosine theta 1, theta 3 dot. And the last but not least is going to be theta 1 dot. You agree with me? This is what it is. Now same drill, and I don't have time to actually code it, but I will do that in next class. But before I do that, I will set this up, and I want everyone to try this problem. So this is the pendulum, the last pendulum. Okay, here is this prismatic joint, and this prismatic joint is attached to this revolute joint. This is the pendulum. Now this is super duper important. So before you go, just wait for a second. This is super duper important. At this point, what I want you to understand is tell me your coordinate system. This is your z-axis, right?
Yeah.
This is z0. This is x0. And this is y0. So omega x is about this. Omega y is about this. And omega z is about this, right? Now look at the pendulum. For the pendulum, you have to assume the exact same axis. This is the key. So for the pendulum, you have to assume the exact same axis. Remember the kinematic diagram that you have drawn? So this is your 0th frame. This is your first frame. This is your second frame. Remember the kinematic diagram that you have? So now understand a slender rod like that. What is the length of this guy? This is L, right? And I'm going to write down the same. This is going to be my X. This is going to be my Z. And this is going to be my Y. So now tell me what is IXX for the slender rod. Tell me what is IYY for the slender rod. Tell me what is IZZ for the slender rod for this coordinate system. This is super important. This is where the students get it wrong. This centroid coordinate system must match the inertial coordinate system. And what is this? Tell me. This is L. So assuming this is a slender rod, which means the length is the most important dimension. This dimension is very small. This dimension is say maybe A. A is less than L. Then what you have is IXX is actually 0. IYY is 1 by 12 M L square. IZZ is 1 by 12 M L square. Assuming this slender rod. For what?
This is assuming 0 radius, basically.
So what that means, There is another way you can assume this, and I need to stop. But there is another way you can assume this. You can assume this a non-zero thickness. And then this becomes like a rectangular beam. And you have to use the IXX, IYY, IZZ for the beam. But whatever you do, this would be X, Y, Z. And I'll stop here.
So we don't take this at an angle. right?
No. Remember, kinematic diagram is the starting point. And even if you take it at angle, moment of inertia will not change.